Hey folks, Dr. Phil here. So this is going to be a video on correlation analysis and linear regression. So let's just jump right into it. So what is correlation analysis? What does the word correlation mean? Well, correlation means something is kind of like linked, associated to something else. So we can think of correlation analysis as a group of techniques to measure the relationship between two variables. So we could study the relationship between two interval or ratio scale variables. So we could start with a scatter diagram. This is I'm sure most of you have seen like a scatter plot, right? Scatter diagram. Um, this is a graphic tool used to show the relationship between two variables. Um, the x-axis is usually for the independent or the predictive variable, and of course the y-axis is the other one, right? The dependent variable or the predictor. So let's look at an example. So North American copier sales sells copiers to businesses of all sizes through the US and Canada. The new national sales manager is preparing for an upcoming sales meeting and would like to impress upon the sales reps the importance of making an extra sales call each day. She takes a random sample of 15 sales reps and gathers information on the number of sales calls made last month and the number of copiers sold. So here we can see the sales reps, we can see the sales calls, and then we can see the copiers sold. So we've basically got copiers sold on the y-axis, right? And we've got sales calls on the x, and all these points have been plotted. So think of these as your ordered pairs, if you will. All right, so hold that thought for a second. The correlation coefficient. So this is a measure, this is a quantitative, a statistical, a mathematical measure of the strength of the linear relationship between two variables. So we can identify it as R, like typically a lowercase r in statistics denotes or a correlation coefficient. It's always going to be from -1 to 1. If it's near 0, that indicates there's very little to no linear association. If it's near 1, that indicates a positive linear association. And then if it's -1, indicates an inverse or a negative linear association. So here you can see like a perfect negative correlation coming down. That would be r equals -1. You see how this is like a perfect line. And then the one over here, this is a perfect positive correlation, right? R equals +1. So think of it like this if we express this as sort of a continuum, we could say that if it's -1, then we have a perfect negative correlation all the way up to the other side. If it's positive, perfect positive correlation would be +1. You're never really going to see like actual results with -1 and +1. It's going to always almost fall somewhere in the middle here. If you get a 0 correlation, that basically says that those variables are not correlated. So there's some examples. We could say there's no correlation between income and number of children. So you notice how these points are just like all over the place. If we said there's a weak negative correlation between price and quantity, if you kind of look at those green data points, you can kind of notice if you look carefully that it does look like it's down sloping, but it isn't. Certainly isn't a straight line, right? Oops, sorry, we go back. And then this was a strong positive correlation between hours studied in school. So like straight away you can look at this one and you can say, yeah, okay, I can see it's kind of going from bottom left up to the top right. So sales calls versus copiers sold. So here with what I've done here is I've kind of like superimposed these quadrants or these lines to make the 4 quadrants here. Um, and you can see if we kind of look at it, yeah, we've got like I mean, obviously it's not a positive one, right? Like it isn't a perfect straight line positive, but you can see that there is a positive slope. Like it is moving up. So what is that saying? It's just saying that, yeah, the more sales calls you make, the more copiers you would sell. Kind of makes sense, right? So here you can see the sales calls. You can see the number of copiers sold. We've got the sales reps on the left here. We've got the differences between the amount and the mean for the x. Think about the x-axis, and then for the y, differences between y and the mean for the y-axis. And then all we have here is we just have the differences. So if we say, for example, like -56 times -4, it's going to give you that 200. Remember to cancel each other out, be 224, so on and so forth. So if there's a strong association, we might be tempted to assume a change in one variable causes a change in another variable. That would be kind of logical, right? But not always, because it could be what we call a spurious correlation. So strong relationships between variables that are not related to each other, but are related to other variables. So it looks like they're related, but it turns out there's some kind of mediating variable, something in the middle that we're not thinking about that's actually causing the differences. So some examples. Consumption of Georgia peanuts and aspirin, right? professor incomes and number of mental institution patients, right? So some of these are like, they're obviously not related. Number of donkeys and number of doctoral degrees, right? So as we're saying, correlation does not imply causation. Just because there's maybe more donkeys in the world, that doesn't mean that there's more doctoral degrees. Or if they're both going up, it doesn't mean that they're related to each other. So let's say you have a strong sample correlation. So could it be the population correlation is zero and the sample correlation just occurred due to random chance? Or is the population correlation actually not zero? So we can figure this out by using a test of significance, right? So we have our, like always, our null hypothesis is equals because there's no change. Our research or alternate hypothesis is we're saying we're postulating that there would be a change, hence the equal sign with the little line through here, the inequality. We have our test statistic. So t equals on the numerator r over the square root of n minus 2, and then on the denominator the square root of 1 minus r squared. So we have a t distribution with degrees of freedom, which is equal to n. N is the sample minus 2. So go back to our sales calls versus copiers sold example. So we come up with an R of 0.865, and we have n equals 15. So I went ahead and kind of put out the null hypothesis and the research hypothesis again. And then you can see here we've got the critical value here, negative 2.160, and then positive 2.160. So if it's in, remember, if it's in this region, we're not rejecting the null, we're actually accepting the null. If it's over here or over here in these areas, these kind of brown shaded areas, if you will, then we're accepting the research hypothesis and rejecting the null hypothesis. So we plug in our numbers, we get a t-value of 6.216. So we can certainly, it's way more, 6.216 is way more than 2.160. So we can certainly reject the null hypothesis and conversely accept the research hypothesis. So we can conclude the sample correlation is too large to come from a population with no correlation. Okay, the other thing I want to talk about just briefly in this video is regression analysis. Regression is a really powerful tool. Very easy to do. It's very cheap. You just reading the output isn't as bad as everybody seems to think. So let's talk a little bit about regression. So regression analysis is another method to examine a linear relationship between two variables. Provides more information than correlation certainly does. And we can estimate the value of the dependent variable y for a value of the independent variable x. So the regression equation could be thought of as an equation that expresses the linear relationship between two variables. So the first question is, how do we get the equation? So we use the data to position a line that best represents the relationship between x and y. So think about these sales calls. This is the data points, the ordered pairs we looked at before. And then you can see like all these different lines. Okay, which one of these is the best line? So the goal of the regression equation is to basically give us the best line of fit, if you will. So it's hard to do that without any criteria, and like I said, it may not be the best line. So somebody might look at this line and say, what if we move it up a little bit or move it down? Then we'd get closer to some points, but further away from others, right? So the goal is to get the line of best fit. So as I said, the best fitting line is obtained by the least squares principle. Remember minimizing the sum of the vertical distance between those lines, right? So the formal definition of least squares principle is as follows: a mathematical procedure that uses the data to position a line with the objective of minimizing the sum of the squares of the vertical distances between the actual y values and the predicted values of y. And that's kind of like what you're seeing here, right? So they're looking at, okay, so which of these lines are the best one? And we'd look at this one in the middle, we look at the one on the right, and then we'd probably say, yeah, the one on the left is probably the closest. So the general form of the linear regression equation is simply, this is what we call y hat, because it looks like a little hat above it, equals a plus bx. So y hat is the estimated value of y for a selected value of x. A is the constant, or the intercept. B is the slope of the fitted line. And then x is the value of the independent variable. You might say this is actually very straightforward. So the values of a and b are given by, so we have b equals r, and then it's just s sub y over s sub x, and then a equals y bar minus bx bar, as we will see. So we previously determined the correlation to be R equals 0.865. So straight away, before we do anything else, we know that's pretty good, right? That's a pretty good correlation, a pretty strong positive correlation. So we got S sub X of 42.76. We've got S sub Y of 42.76. We've got X bar 96. And then we've got Y bar, so the mean 40, and then the mean of Y 45. So the question then is, what is the least squares equation? And then the second question is, and this is where you see like the value of this equation. If a salesperson makes 100 calls, how many copies do they expect to sell? So this is literally right from the last slide. And you can see here where just again, don't be intimidated by these formulas, just plug in your numbers. So we get B of 0.2608, and then we get A equals 19.96. So we have a least squares line, so it's Y hat equals 19.69 or 19.96, and then plus 0.2068x. Okay. So if B equals 0.2608, for each additional sales call, the salesperson can expect to increase the number of copies sold by about 0.2608. So if a salesperson makes 100 calls, then we just plug the numbers into the formula. Y equals, remember, 19.69. Think of that as the intercept, plus 0.2068 from the least squares line, and then multiply by the 100. And then we get 46.0432. So basically, you make it, if the salesperson makes 100 calls, they can expect to sell, just say about 46 copies. Now, in the previous example, we found that B equals 0.2608. Now, what if that occurred by a random chance? What if the population value actually turns out to be 0? So let's let B, beta, represent the population slope. So now I'm adjusting my null hypothesis slightly. I've got H sub 0, beta equals 0, versus I'm now saying that beta is not equal to 0, right? So let's say we reject the null hypothesis. We're saying that a significant relationship exists between the variables and that the regression equation is able to predict or forecast the dependent variable. If it's not rejected, then there's no merit to use the independent variable. So that would be like saying, all right, well, remember the H sub 1, what is that? That is the research hypothesis is saying that P is not the same, the probability is not the same as 0. So as we can see, we have our formula up here, right? We have our null hypothesis, beta equals 0, versus our research or alternate hypothesis, beta is not equal to 0. We have a test statistic, T, which is B minus 0 over S sub B. We have a T distribution with degrees of freedom equals N minus 2. So again, what is N? N is just the sample size. We're just subtracting 2 to make it a little more conservative. And then S sub B is the standard error of the slope. So if we look at the computer output for this, you can see down here, we've got there's your multiple R, 0.865. We've got R squared, 0.748. We've got an adjusted R squared, which is 0.728, which is good. We have our standard error, 6.72. And then we can see, if we look down here, we've got the sales calls. You can see down here, 0.2606 for the coefficient, about 0.004 for the error. And then we have a t-stat of 6.2. So if you remember, we said that y prime equals 19.69 plus 0.2068x. So what if we want to test for a positive relationship? So now instead of like the multi-directional, we just want to test a positive relationship. So we got t equals 0.2606 minus 0. Remember that b minus 0 over 0.04. So what do we get? We get 0.620, excuse me, let me say that again, 6.205, there we go, with degrees of freedom equal to 15 minus 2, sample size minus 2 equals 13. So again, using the alpha of 0.05, the critical value is 1.771. So obviously, the value here is higher, 6.205. 6.205 is way higher than 1.771. So we're certainly okay to reject the null hypothesis. So we can conclude as the number of calls increases, the copier sales also increases. All right, so moving on. Is the regression equation a good predictor of Y? So we can never have perfect predictions, obviously, just like the weather, right? They can't predict it perfectly. We need a measure of how precise the prediction of Y is. This is where we get what's called the standard error of the estimate. So think of this as a measure of the dispersion or scatter of the observed values around the line of regression for a given value of X. And you can see the formula here. So if it's small, The data are close to the line, and we would thus use the equation to predict. If it's large, the data are widely scattered, so we're not saying we couldn't use it, but it's going to be much less precise. So as you can see here, if I plugged in my numbers, what do I get? I've got my standard error here, 587. Plugging it back in, 8 over 15 minus 2, that's the sample size minus 2. That's kind of speaking to degrees of freedom. And I got 6.720. So that's actually not too bad. Okay, you can see here just so you know it's there as well. This is actually on one of the previous slides I showed you, but I'll just show you again real quick. The standard error is 6.720. Okay, so ultimately what we need is we got a lot of output, we got a lot of fancy numbers, but we need something, as it says, that's easy to interpret. This is where the coefficient of determination comes in. Perhaps you could arguably one of, if not the most important output statistic of a regression. So the coefficient of determination. This is formally defined as the proportion of the total variation in the dependent variable y that is explained or accounted for by the variation in the independent variable x. So that probably sounds like gibberish. This will make a little more sense in a second. So the correlation squared is, of course, r squared. It's always going to be between 0 and 1, from 0 to 100%. And it is, of course, based on an ANOVA analysis of variance framework, right? So we can actually skip past this one. Yeah, here we go. So I want to make sure we see this. So you can see here, like we've got the r squared, 0.748. And then you can see we've got an adjusted r squared right here of 0.728, right? So think about why the coefficient of determination is important, because we're basically saying all these variables over here, all these independent variables, collectively account for this much variance of the dependent variable. All right, so just some assumptions about regression. One, we're assuming when we do a regression that the data we have follows the normal distribution, right? Just that, again, the bell shape, the bell curve. Number two, has a mean on the regression line. Number three, has the same standard error of the estimate. And then number four is independent of the others. Okay, interval estimates are predictions. So I want to just talk briefly about the confidence intervals. You may have learned about these if you've taken like a basic statistics class. So we're going to predict the mean value of y for a given value of x. And we have a formula like always. I know I say this all the time. Don't be intimidated by these formulas. I promise it's just plugging in the numbers. So we can predict an individual y for a given value of x. And for a given x, prediction intervals are likely going to be wider. So sales calls versus copies sold, back to the previous example. So if we wanted to compute a 95% confidence interval for the mean sales when the number of calls is 50, we want to compute a 95% prediction interval for the sales when the number of calls is 50. We've got all the data here that we need to do this. So sales reps, as always, most of this is the stuff we had before, right? Sales reps, sales calls, copies sold, the variance in x and the variance in x squared. So if you remember, RS was crit was 6.720, y prime was 19.69. This plus 0.2068x, that was the regression equation. So for x equals 50, if y prime is 19.69 plus 2.068, plug in the 50, we get 33.0032. And then we have degrees of freedom, which if you recall, sample size 15 minus 2 plus 13, so t was equal to 2.160. That's all from a previous slide. So with a 95% confidence interval, again, we just plug in our numbers, and the confidence interval gives us what? 27.4 up to 38.6 copiers. With a 95% prediction interval, 17.4 up to 48.6 copiers. So think of this as kind of like we're saying it should be this, right? Like in this case, the regression equation says 33, but it could be as low as say 27.4. It could be as high as 38.6. And this is kind of what they're showing you on the graph here. So you can kind of think of these green lines represented. So the green lines represent the intervals, and then the red lines represent the confidence intervals. All right, as always, thank you for watching, and I will see you all in a future video.